In today's video, we're going to perform a linear regression and a nonlinear regression to obtain the unknown coefficients of the Antoine equation for water vapor. And to do this, we need data for the vapor pressure and the temperature values. Before we dive into today's topic, I would like to give some background about the relevance of the Antoine equation to a phase diagram for a pure substance. So here on the screen, I have the phase diagram for water, as well as the Antoine equation below. And what the Antoine equation does is it relates the vapor pressure to the temperature along this vaporization curve labeled here, from the triple point to the critical point. And that is what the data is going to be coming from that we end up using to do the linear regression and nonlinear regression in Python later in this video. So what we need to realize is that for a pure substance, in this case it would be water, that we have in some sort of vessel, there is an equilibrium established between the liquid water and the water vapor. And because of that equilibrium, we can model the relationship between the pressure and temperature along this vaporization curve here, wherein the temperature of the liquid water is going to dictate the vapor pressure of the gaseous water above that liquid. So that is what's modeled here by our vaporization curve, and hopefully that gives you a little bit of background as to how these coefficients A, B, and C are relevant in helping us understand the relationship between the temperature and the vapor pressure of the water, because the whole point of doing the linear regression and the nonlinear regression to obtain these unknown coefficients is to model the relationship between the vapor pressure and the temperature. And that model ought to look something like this vaporization curve, because that's what's actually happening physically, is there's this equilibrium between the liquid water and the water vapor. Before performing a linear regression and a nonlinear regression in Python to obtain the unknown coefficients for the Antoine equation based on vapor pressure and temperature values, I would like to give more background information on linear regressions in general. A linear regression involves obtaining the unknown coefficients for a model equation by solving a linear system of equations. I would like to demonstrate this process with a very simple equation first, before we examine the Antoine equation. Let's look at the equation y equals mx plus b. The key thing to understand when solving this linear system of equations that I mentioned is that a linear regression is done by solving a linear system of equations in which we have a design matrix multiplied by a vector of unknown coefficients set equal to a column matrix of what will be known values. And this is going to be modeled on our equation y equals mx plus b. And when I explain the rules for multiplying matrices, all of this will start to make sense. Now we're ready to start making our matrices. So I'm going to begin with the design matrix. In the first column, I'm going to store all of my x values, which could be any number of x values here. So I'll start with the first x value, and then that will go all the way down this column to the nth x value. And then I'm also going to make a column of ones. And like I said before, when we're solving this linear system of equations, we have to have a design matrix multiplied by our vector of unknown coefficients set equal to a column matrix of our known values. So our unknown coefficients here are m and b. And we have two unknown coefficients. So I could store them in a 1 by 2 matrix or a 2 by 1. I'm going to store them in a 2 by 1 matrix. So we're going to multiply that by our design matrix, and then we have m and b. And then this is set equal to our column matrix of our y values, which we do know because they're data points. And the number of y values can also be any number, but it will correspond to our number of x values there. So y1 all the way down to the nth y value. Okay? So the key thing to understand when we're performing matrix multiplication is that we're going to multiply each column by the row of the other matrix. And what this means is that the inner dimensions of two matrices being multiplied must match. Notice that I decided to make the vector of our unknown coefficients, m and b, a 2 by 1 matrix instead of a 1 by 2 matrix. Let's see if I made the right decision by looking at the dimensions of each of our three matrices. This design matrix has n number of rows and 2 columns, so this is an n by 2 matrix. Our vector of unknown coefficients, like I said before, is a 2 by 1 matrix. And our column vector of our known y values is an n by 1 matrix. And as we can see, the matrix multiplication we have set up for our linear system of equations here is valid because our inner dimensions, meaning the columns of this matrix, match the row of this matrix, 2 and 2. And the resulting matrix is the product of our outer dimensions, n and 1, which corresponds to our column vector of known y values. So what I'm going to do next is try to actually find the values for our unknown coefficients m and b. But we do have a problem here. As you can see, we have n number of equations, but only 2 unknown values that we're trying to find. What this means is that our linear system here is overdetermined because we have more equations than unknown values. Because we have 2 unknown values, we need to manipulate this linear system of equations such that we have 2 equations and 2 unknowns. And the way we're going to do that is by multiplying each side by the inverse matrix of x. It's similar to what you would do in Algebra 1 when you're trying to isolate a single variable. For example, if I were to represent this design matrix as x, my vector of unknown coefficients is y, and my column vector of known y values as z, we would have this equation here, x times y equals z. And if we wanted to find y, we would multiply each side by the inverse of x, which is x raised to the negative first. And what that would do is cancel out our x values, and it would isolate the value we're trying to find, which is y. What we're going to do with the matrices is something quite similar. But instead of just canceling out variables and isolating a single variable, we're trying to find the value of the unknown coefficients m and b by setting up a linear system of equations such that we have 2 equations for our 2 unknown values. And I will demonstrate that that will be the case by examining the dimensions of each matrix that is involved in this multiplication when we multiply each side by the inverse matrix of x. And also note that the inverse of our design matrix x here is also known as the transpose of x. So I'm going to actually refer to this design matrix x as x sub t. So let's start this by denoting our matrices. So we have x times y equals z, like I said before. And then I'm going to multiply the left-hand side by the transpose of x. And I'm going to multiply the right-hand side by the transpose of x. There is something important here that I do need to mention. That matrix multiplication is actually not commutative, meaning the order does matter. So when I multiply this right-hand side, similar to the way I multiply this left-hand side of the equation, the transpose of design matrix x actually needs to be first. And you'll actually see that when we examine the dimensions of each matrix and show that we do obtain 2 equations with 2 unknowns such that we can solve for the unknown values of m and b. So I'm going to just erase z real quick and write transpose of x here, x sub t, times z. Okay, so let's examine our dimensions and see if everything checks out. So the inverse of the design matrix X is just going to be the opposite dimensions of this design matrix X, which is n by 2. So we're going to flip that to make it 2 by n. So we have a 2 by n matrix multiplied by our matrix X, which is n by 2, multiplied by our vector of unknown coefficients, which is 2 by 1, set equal to the transpose of X. Once again, that's a 2 by n matrix, multiplied by Y, which is an n by 1 matrix. And what you can see here is that the result of the transpose of X multiplied by the design matrix X results in a 2 by 2 matrix. These could be any values. I'm just going to put X's. Okay. So this is a 2 by 2 matrix there. Then we have our vector of unknown coefficients. Notice that the multiplication is still valid. The inner dimensions of these matrices being multiplied all match. Okay, so we would have our vector of unknown coefficients, m and b. And then the result of this would be a 2 by 1 matrix of some values. I'm not exactly sure what, it would depend on our data. So as you can see now, we can obtain the unknown coefficients for m and b because we have 2 equations and 2 unknown values. And remember, if this looks a little confusing, the way matrix multiplication works is we're going to multiply the column by the row of the other matrix. And I might have neglected to mention, that was the whole purpose of having this column of 1s here in the first place. The column of 1s is going to be multiplied by the y-intercept denoted as b. And notice that b is by itself. It's not multiplied by any y or x variable. So that is why we have the column of 1s. So now I think we're ready to do the same thing with the Antoine equation. So I'm going to take the time to erase all of this. And what we're going to do with the Antoine equation is extremely similar. The only difference here with the Antoine equation is we have 3 unknown coefficients that we're trying to find, a, b, and c. So let's take a look. The Antoine equation is defined by the log base 10 of our vapor pressure values equal to coefficient A minus B divided by C plus the temperature T. So you might be looking at this and thinking to yourself, how the heck is this an equation that we can do a linear regression for? But remember what a linear regression is. It involves obtaining these unknown coefficients, in this case A, B, and C, by solving a linear system of equations. And the linear system of equations has to have a design matrix multiplied by our vector of unknown coefficients set equal to a column matrix of known values. And what you're going to see is that we're able to manipulate the Antoine equation such that we can set up that design matrix multiplied by the vector of unknown coefficients set equal to the column matrix of known values. So let's start to figure that out. We can start this by trying to isolate our unknown coefficients on one side of the equation. So I'm going to start this by multiplying each side by c plus t. And also for simplicity, I'm going to write the log of p, which you can hopefully think of as the common logarithm, log base 10, just to save time and not have to write 10 every single time, which might get confusing. So let's multiply each side by c plus t. So we have the log of our pressure times c plus t equals A times c plus t minus b. Okay? And we can distribute our terms here. So let's see what that gives us. we have the log of pressure times C plus the log of pressure times T equals AC plus AT minus B. Excellent. And now that we've done this, we can rearrange our terms a little bit to get all of those unknown coefficients on one side. And we obviously did the same thing with y equals mx plus b. The only difference is that y equals mx plus b is such a simple equation that the unknown coefficients m and b are already on one side, which made everything a lot easier. So we have C, A, and B. So we want all of those on one side. And notice here that we have the log base 10 of our pressure times temperature. And because we are going to have data values for pressure and temperature, I will give you a hint and say that the log base 10 of the pressure times the temperature, these values are going to form our column matrix. So what we're going to have here is, we'll write this on the left side. So we'll have A times C minus B. Because these are all our unknown coefficients, I'm going to just group them all together like that. I didn't do anything to them. I just moved the minus B term over. And then I'll add A times T. We'll subtract log of P times C from that side, and then we'll set all of this equal to the product of log P times T. Excellent. Now we have this set up so that we can create a design matrix multiplied by our vector of unknown coefficients set equal to a column matrix of these known values. And note that we have n number of pressure values and n number of temperature values, which allows us to create a column matrix of the log of the pressure times the temperature. So what about this left-hand side? How are we going to make this design matrix and have our vector of unknown coefficients and have valid matrix multiplication? Well, we do have A multiplied by T. So let's start there. So let's start by making our design matrix have a column of our T values. All the way down, T1, all the way down to the nth temperature value. And then we have our our coefficient, C, multiplied by the negative log base 10 of our pressure values. So because the negative log base 10 is simply an operation that we can perform on our data points, I'm going to include that in the next column of our design matrix. So I'm just going to write negative log, it'd be the base 10, of the first pressure value all the way down to the negative log base 10 of the nth pressure value. And once again here, we are going to need a column of ones because there will be an unknown coefficient here that we need to solve for that's not multiplied by any variable, and that's AC and then minus B. And you might see this, that we have a bit of a problem here because we have A times C. We have B, which is great, but we also have A times C. What I'm going to do to get around this is just represent AC minus B as D. So we'll call that one unknown coefficient D. And then what we can do, especially when we solve this problem in Python, is actually use this equation to solve for B in the end. So for now, we're going to represent A times C minus B as an unknown coefficient D. So that means we need our column of ones, and now we have to make our corresponding vector of unknown coefficients. So the first column here is going to be multiplied by the first row. Our temperature values were multiplied by A, so A is going to be first. And then our second column, second row, we had C. So that's two of our unknown coefficients. And then our column of ones is the third column. So our third row, our coefficient, we'll use D. And then this is all going to be equal to a column matrix of known values of the log of P1, log base 10 times our first temperature value all the way down. Okay. So once again, we have our design matrix, our vector of unknown coefficients, and our column matrix of known values. We obtained the three unknown coefficients, A, C, and D, and then used D, C, and A to solve for B, using the same process that we used to find the unknown coefficients M and B for the linear equation that I did before. We would multiply each side of this linear system of equations by the transpose of this design matrix here. And what this would do is create a 3 by 3 matrix multiplied by our vector of unknown coefficients set equal to another column matrix of 3 known values there. And once again, we would obtain a situation where we would have 3 equations and 3 unknowns instead of n equations and 3 unknowns. So by multiplying each side by the transpose of the design matrix, just like we did with the equation y equals mx plus b, we are able to find the unknown coefficients because we get rid of the situation where we have an overdetermined system of linear equations. So I'm not going to go through that again because we just did that with the equation y equals mx plus b. But what we are going to do is use Python code to do exactly what I've shown here on the whiteboard with the Antoine equation. The only difference is that we're going to have actual vapor pressure values and temperature values for water so that we can obtain unknown coefficients for the Antoine equation for water vapor, which will be A, B, and C. Now we're ready to perform a linear regression in Python to obtain the unknown coefficients of the Antoine equation for water vapor. But first, we need to get pressure and temperature data. So right here, I have water vapor pressure data in a CSV file, which the CSV just stands for comma separated values, which will become important for us later. So I'm going to select the file here, and I have a web page. And what I need to do is I need to download this data into Python so that I can load it as a text file, and then I can store the temperature values and the pressure values in Python. And what that will allow us to do is actually plot the points and make a scatter plot, just like you can do on a TI-84 calculator. Now, the one problem with this link here is that this is a link to a web page, and I just want the data because that's not going to work if I just have a web page here. So what you can do here on GitHub is you can select raw, and that gives us just a text file here, and that's exactly what we want. And then before this, so I'm copying and pasting my link here, I actually looked up how to download HTTPS with Python command. And what I found is that you can actually use the wget command. And we just have to make sure we start this off with an exclamation point, wget, and then we just put our link, so Control V, there it is, Shift Enter, and now we're ready to go. So as I make this program, we're going to use numerical Python a lot, which is a very useful Python library, especially when you're working with arrays, which are also matrices in this case for us, because we're trying to perform a linear regression. So now I'm going to import this into our code. It's abbreviated by NumPy, N-U-M-P-Y, and we'll import it as NP for short. So now that that's imported, we can also use other functions within NumPy to actually help us perform the linear regression. And that doesn't just include matrices, actually. So in this case, I'm actually going to use NumPy to help me load the text file. So let's call this file data, because that's what's within the text file is our temperature values and our pressure values. And we'll specify this as np.load.
And all we really have to do here, as it says, is just put in the file name in quotes. So that would be water vapor pressure. Make sure I spell it right. CSV. Shift enter. And we do have an error. So there's a couple things wrong here. So one thing I didn't specify here that I see is that this is a text file that I'm trying to load, because this is from here. This was a text file. And I didn't put anything here. I just said load. So Python doesn't even know what the heck I'm doing. So let's add that and see if that fixes the problem here. Well, it just moved us to a new problem. It said that it could not convert string to a float. So it believes that the data type should be a float, but it cannot convert a string to the float. And the reason this thinks that this is a string is actually the comma, because this CSV stands for comma separated values, which means that our values in our text file are separated by a comma. But that creates a problem for Python that wants these to be floating decimal values, which they would be, except there's a comma in between. So to get rid of this, we need to see what this load text allows us to actually do. So I'm going to try to hover over it here. And if you look, we have dtype, comments, and then delimiter. And what delimiter actually means is it's what's in between your values within the text file. And here it says none because, I didn't specify anything there. All I did was put in the file name. But we actually do have something in between our values that we need to get rid of, and that's the comma. So to do that, all we're going to do here is put a comma here and then type delimiter and set it equal to a comma in quotes. And now everything's all good. Okay, so this is very good. So now that we have the file loaded into Python, we want to store the temperature values as a list in one variable and the pressure values as a list in another variable. So let's do that. Let's start by making a variable temp. We'll set it equal to data, which is our text file, which is 2 columns. And notice that this first column has temperature values, as we can see, because we have 2.93 times 10 to the second power, which is 293. So these are probably the temperature values in Kelvin, which is exactly what we want. But we want all of the rows for that first column. If we want all of the rows, we need to index this by putting a colon, and that will iterate through each row. And then we just need to specify what column we want. And for indexing in Python, we actually start at 0. So because I want the first column, I'm going to put a 0 here for the column index. Now let's do the same thing for pressure. We'll call this press equals data. And then once again, we want all the rows, but we want the second column, and this will be indexed by a 1. So now we're ready to go. And the next thing we're going to do is we want to plot our pressure and temperature data. And then we can perform a linear regression to model that data on a graph here. To perform a linear regression on the pressure and temperature values that we have, we need to use some sort of graphing tool to make a scatter plot, and then we can make our line to model the data. So to do that, I'm going to use Plotly, which is another Python library, and I want to make a subplot. So we're going to specify from plotly.subplots import make subplots. And this is just something that is really commonly used because it makes really, really beautiful plots. And then I'm going to actually go up here. I don't know why I have parentheses on this. And hit runtime all. And what that's going to do is it's going to run all my commands in order. And this is just good practice because it will make sure that Python doesn't indicate you have an undefined variable or something like that just because you haven't run everything in order because you've been busy writing extra code. So I might make that mistake in this video, and I will hopefully be sure to catch it as I make that error. So let's add new code here to make an actual scatter plot. So let's call our function here. So we'll just define it as figure, and we'll set this equal to make subplots because that's what we imported this in. And then because we're calling this function, we do need the parentheses there. So there is that. And then we can do figure.add scatter. And this allows us to specify our x and our y and all the other things that will be associated with our scatter plot. But we're just going to try to keep it as simple as possible. And all of this are various things that you can look up online. So I was just looking at Plotly Python library, and as you can see, it's a graphing library for Python, and it makes really, really cool graphs. So these are things that you can look up, obviously. So for our x-axis here, we're going to have our temperature values. And we already have those stored in a list, so we can just set x equal to temp. And then we have our pressure values. And I'm actually going to change something here because when we made our design matrix, we used the negative log base 10 of our pressure values. Now, what I would like to do here is actually do log base 10 of the pressure values, but I would want to keep it positive actually, because I want this linear regression to be shown in the first quadrant because it just looks nicer. But we do have to keep in mind that we did use the negative log base 10 of the vapor pressure values for a design matrix, but that will come up here in a second. But first, let's change all of our data to the log base 10 of these pressure values, and we can use that using NumPy. So let's do np.log. And notice here, it gives us a lot of options. We're actually going to want to use log 10. If we use log, NumPy is going to believe that you're doing the natural logarithm, and that is not what we want. And if you don't believe me, I'll do that here. And if you see it here, should come up. There. It says it's the natural logarithm. So we do not want that. We want log base 10. So we'll put that. And then to remind us within our variable name that this is the common logarithm of the vapor pressures, I'm just going to put log press. And then we'll make that equal to y. So that's what we're going to be graphing, is the log base 10 of all those vapor pressure values on our y-axis. Okay? And then I'm going to keep everything as simple as possible. So for our mode here, what we can specify is markers. And that's just going to be exactly what we want, because all I want to see here is just a scatter plot of the data that we have. And there you have it. So there's the data there. Looks pretty good. So yeah, we have the log base 10 of the vapor pressure values and then the temperature values. So what we need to do next is the more complicated stuff. We need to make a design matrix. And this is another special thing that NumPy is capable of doing. It has a nice feature here where it can take the list that we have of our temperature values and our pressure values and that sort of thing, and take those lists as columns for one array. And that array is going to be our design matrix. So that's what I'm going to do next here. And let's use the same notation that I used on the whiteboard. So we'll specify our design matrix as x, and I'm going to set this equal to numpy np.c underscore. And that's what's going to do this for us. And then because this is an array, we'll use the square brackets there. And so if we remember, our first column of this design matrix was just the temperature values, nothing complicated. So we'll put in temp, separate it by a comma, and then now we're going to have to specify the next list that's going to form our second column. And this is where we have to be careful, because now I do actually remember that we did the negative log base 10 of our pressure values. So we can do that by just doing negative log press, because log press is the log base 10 of all our vapor pressure values. The next thing we need is our column of ones. So to do that, there's another function in NumPy we can use, and that's np.ones. The issue with this, though, is that we actually need this column of ones to be the same length, the same number of rows all the way down, as our temperature values and the negative log base 10 of our pressure values. So to do this, we see there at the bottom of the screen here, there's np ones like. And what we do here with the like is we specify a list so that it is actually the same size. So let's just put in temp, that way it's the same length. Awesome. So now we have created our design matrix. The next thing we're going to do using NumPy is extremely effective because it's going to allow us to find the vector of our unknown coefficients. Now remember, this vector of unknown coefficients is going to output a 1x3 array. But this array will only have 2 of the unknown coefficients we're looking for. We're looking for A, B, and C. But if you remember, I specified an unknown coefficient D to take the place of the product of A and C minus B. So now we want to do matrix multiplication to find the unknown vector of these coefficients. And we can do that using np.linalg.solve. And what this function takes is it's going to take basically the left-hand side of our equation A and the right-hand of our side of our equation B. Now, when we're trying to find the vector of our unknown coefficients, we had to make the left-hand side equal to the design matrix multiplied by the transpose of the design matrix, and the right-hand side was our vector of the temperature values times the log base 10 of the pressure values times the transpose of our design matrix X. So that's what we're going to specify here. And what that would result in would be our vector Y. So I'm actually going to call this Y. Let's do that. So we'll say Y, our vector of unknown coefficients, is equal to np.linalg.solve. So the left-hand side of this would have been x.t, and that's what we use for the inverse matrix of our design matrix that we've created. And then to multiply matrices in Python, we actually use the @ key there, so shift and 2. That's not one I commonly use unless I'm typing out my email. So we're going to multiply that by our design matrix on the left-hand side, and then on the right-hand side, we are going to multiply the transpose of the design matrix X by a matrix of the temperature values times the log base 10 of our pressure values. So we have to be very careful here. I can't just write temp times log press. Even though that is what we're doing, we need to keep those contained because the product of these two values is one single value that, those individual values are going to form that one column matrix. And we want to keep those together. So I'm going to put those in parentheses. And those will form a column matrix because we know that they're already the same length because we loaded them from our text file. So we don't have to worry about any of that. So now we should be good to go. So you might be thinking here, okay, that's all well and good. It seems like we've made a lot of progress, and we definitely have. But one thing I want to figure out here is, well, it gives me a green check mark, but what are my actual values? Like, did I get those unknown coefficients? And we can do that in Python by actually unpacking an array. And you do that by setting the array equal to a corresponding amount of variables. And we can do that because we had 3 values. There's 3 values stored in this unknown vector, this vector of unknown coefficients, y. And we defined those as A, C, and D. So we can unpack this by separating each of these as commas, or by commas. So we'll do A, C, and D. And what this will allow us to do is when we do calculations with our unknown coefficient variables that we find, we don't want to have to constantly index that vector that we have those values stored in. Because if I just left this as y, I would have to use y index 0 from my first value, that sort of thing. And that's just extremely confusing and difficult to read for your code, or for anyone reading your code. So unpacking is extremely useful in that regard. So now I can do A, shift enter, and there we have a value, B, C, shift enter, and D, shift enter. And I'm glad I actually made the mistake of putting B, because that reminds me that we need to actually find what B is. So I'm going to just delete these real quick, and let's make a line to compute B. So we had D equal to A times C minus B. So if we just flip that around to solve for B, we would have B equal to the product of A and C minus D. So now we have our B value. So now we're basically ready to add a line to fit through our data points. And that's going to be the linear regression. So I'm going to copy and paste this down here so that we can add everything. Now, we already have our temperature values. That's all well and good. But now that we have the unknown coefficients, A, B, and C, for the Antoine equation, we can use that to compute the pressure values that we're going to use to make our model line to fit our pressure and temperature data. So y is not actually going to be equal to the log of the vapor pressure values from our data. We're going to compute new pressure values based on the unknown coefficients for the Antoine equation that we've found. Because the whole point of this is to use those unknown coefficients to model our data. And so we need to create those model pressure values. And let's keep everything simple. We can keep y equal to the log base 10 of those pressure values. So I don't have to do 10 raised to the power of the Antoine equation. I can simply just do A minus B divided by C plus temp. And that is going to correspond perfectly to what we want, because we're going to have model log base 10 pressure values that are going to create a line. And then for our mode here, we're just going to change this to lines, because I want this to be a line through the data. That's exactly what I'm looking for here. So yeah, let's do that here, and shift enter. Boom. So there we have it. And if we look closely, this data is pretty good, but if you look between these two data points here, there's kind of like a very, very straight line. And that's not really something that we want to see, because we want this to be a smooth curve to model our data, because that way we can figure out what certain pressure or temperature values could be within our data set, within our range of temperature values. But we also want this to model the change of pressure and temperature so that we can actually interpolate values as well. So the problem that we have here is that with our temperature values, we're using X as temp. And that means that we're using these values from the text file. And the issue that creates is that those values are not separated by equal increments. So to make our line for this regression, we do want temperature values that are separated in specific increments. So that's exactly what I'm going to do here. And the way I'm going to do that is by creating a new temperature variable. And actually, I'll just do that right under B right here. So I'll put add code there. And let's call this new temp. And once again, we're going to use NumPy. So let's let this be NP. And there's a really cool function within Python, and we'll use numerical Python for this, called linspace. And using linspace, we can create a set of temperature values and space them out equally. So that way we have a nice smooth curve when we make this model line for our data here. So let's do that. And since our temperature values are in Kelvin, we'll start a little below at 250 Kelvin, which is just a little bit below specifically the freezing point of water, which is 273.15. And we'll go all the way up to, let's see how high this goes. Looking at the data here, it goes to about 650, so let's do that. So here we've specified our minimum and our maximum, basically our range, right? And then the third thing we just need to specify is the number of increments. So it's going to divvy up these values in certain increments. And let's just do like 200 values. It really doesn't matter, but you want enough so that we can see the spacing and that our line is smooth. Now that we have our new temperature values that are spaced out in equal increments, we can recreate our model line through these data points. So all we have to change here is change our x equal to new temp, and also within the equation for y, put new temp in there as well. And if I run all these commands in order, we get our linear regression. And so this will model our data there. And that is exactly what we want to see. And this model line was computed based on the unknown coefficients of the Antoine equation that we found by solving a linear system of equations by matrix multiplication. And we can see what those values are that we obtained here. So let's see what we got. So for A, that, B, and C. Okay, so those are the values that we obtained for the linear regression. And now I'm going to transition into the second main part of this video, in which we're going to perform a nonlinear regression to hopefully obtain the unknown coefficients of the Antoine equation for water vapor using the same pressure and temperature data once again. To perform a nonlinear regression to obtain the unknown coefficients of the Antoine equation for water vapor based on this pressure and temperature data, we have to minimize the sum squared error. So let me explain what the sum squared error actually is. Let's start with the last word there, error. So the error is the difference between the log base 10 of the pressure values from our data, so the log base 10 of these pressure values, which is represented by the blue points on our scatter plot. But then we also have the log base 10 of model pressure values that were used to create this linear regression line. So with these blue little dots here that are our points, our data points, there are some of those points that lie above the red line and some that lie below. And the vertical distance between the point and the line represents the error. So that is what I'm referring to when I talk about the sum squared error. But what we want to do is compute all of the error that we have. And that is why we have to square everything, is because you have some points that lie below the line and some points that lie above the line. So there is going to be some that if you just use the same equation to find those differences, some will be negative. And if you summed all of that up, that would not accurately represent all of your error, because you would have some negative differences canceling out actual positive differences. So it would make the totality of your error be artificially low, and that's not what we want. So instead of using absolute value, which we could use, we'll actually square it, because that's what's most commonly done in engineering practices. So what is actually happening, though? That's one question I had when I first learned about this. What are we actually doing? So the way we're going to obtain the unknown coefficients for the Antoine equation is by minimizing a function. And by minimizing a function of the sum squared error, we determine the ideal values of A, B, and C for the Antoine equation that are going to best model our pressure and temperature data such that the error between our data points and our regression line are minimized. So that is exactly what we're going to be doing here. So to do this, we are going to use another library, and this is called SciPy. And SciPy has a lot of really cool things that you can look up online as well. And we're going to be doing an optimization. So from scipy.optimize, and we're going to import minimize, and that's going to be what we use to minimize our sum squared error here. So we have that, and I'm going to scroll down here, and I'm going to start making a function. So let's define a function. We'll call it SSE in all caps for sum squared error, and we want to make our arguments we want to make this a vector array that contains the three unknown coefficients of the Antoine equation that we're trying to find. So that's what I'm going to do here. Make sure you have a colon for the function there. And we're going to unpack it again. So that way we have each value assigned to the letters A, B, and C within our vector W. Okay, whoops. And then we want to return the sum squared error. So we don't really know what these coefficients are for A, B, and C. That's why we have to minimize this function that we're going to write. And that's what we want to return. So to start, let's start by defining what our error actually is. So once again, it's the difference between the log base 10 of our actual pressure values from our data, and then we have our log base 10 of pressure values that we computed to make our linear model, our regression line here in red. So there is a difference between that. So let's start by computing our model values for the log base 10 of the pressure, which for that, we'll just use these unknown coefficients. So it'll be A minus B divided by C plus our temperature values. So that's all those temperature values from here that we're using once again. And so these are certain values, and we're going to subtract those from log press, because this has all of our actual pressure values, all the log base 10 of all of these actual pressure values. So effectively, this represents our blue points, and then this represents our model, our red points. So that is our error. And obviously, these differences across each item in the rows, some are going to be negative and some are going to be positive. So that's why we want to square this first before we do our sum. We could also do the absolute value, as I said before, but it's much more common in these engineering practices for us to do the sum squared error. So that's what I'm going to do here. So we have that, and now all we have to do is use NumPy to actually write this as a sum. And I don't know why I did this, but I capitalized return. I think it just means I really mean it this time. But there it is. So we have that. So now we have our actual sum squared error function, and all we need to do is minimize that. So we need to use minimize. And here we just need to specify our function and then some guesses, right? And we are going to have to put in guesses for our vector W. So that vector has three different parameters, A, B, and C, which are unknown coefficients of the Antoine equation. So I'm just going to enter in ones for those, just as our guesses, so that the minimization can take place, basically so that the function runs properly. So let's start this by putting in our function, which is just SSE and comma, and then we'll put this in as an array because that's what we have. We have a 1x3 array of A, B, and C. So 1, 1, and 1. There you have it. So it gives us the minimum function value, a message telling us that the optimization terminated successfully, which is awesome. But down here we have that array, and that has A, B, and C in it, and that is exactly what we're looking for. So these values of A, B, and C are values for the Antoine equation, such that if we use these values to make another model line for our data, the error between the log base 10 of our data values for pressure and the log base 10 of our pressure values based on our model line, that will be minimized if we use these values for A, B, and C. So to get these values just by themselves, we want to do dot at the end of this for whatever we want. So if I want to see the message, I can do dot message. Tells me it terminated successfully. But we want X because X had that array in it. And I want to compare that. And there it is. So we see that there. And then we can define this and actually unpack it just like we did before. This time we'll do let's just be safe and do letters we haven't used. So let's do G, I don't even know the alphabet anymore. E, F, G. Let's do that, huh? Let's try that. And then now let's do E, G, F, and G. And what I could actually do here to show you that I did actually compute the unknown coefficients for the Antoine equation for water vapor successfully by doing linear regression and nonlinear regression is I can actually look at the difference between these values. So like A minus E, it's very small. We could also do B minus F. It's a little bigger, but the numbers are bigger. So by proportion, that's with numbers that are in the 1000s. So yeah, you have 1771, and I believe it was 1776 or something. Or 56, sorry. So as you can see there, the difference is very small. So what we have done here is we've successfully computed the unknown coefficients A, B, and C for the Antoine equation for water vapor based on the pressure and temperature data that we obtained in the beginning of this video. So I hope that helped you understand a little bit about how linear regression and nonlinear regression can be used to find unknown coefficients for a model equation given a set of data.